Welcome to Chapter K. We've got 6 lessons in this chapter. We're going to start with our first one off here, and the title of it is called Tangent Lines. And now you might think we have heard of this term tangent before with sine and cosine, but unfortunately, why mathematicians a long time ago couldn't come up with a different name for a different topic, I don't know. But we will talk about what tangent lines are, and they are completely unrelated to sine, cosine, and tangent. Now, the thing to notice here on this title screen is that all of these lines are tangent. So based on that picture, and this picture here as well, what do you think a tangent line truly is? And if you think it might be this, that a tangent line touches any curve at exactly one point. And by curve specifically in this chapter, we are meaning a circle. Now later, if you ever get to calculus, you can certainly discuss having a graph of maybe a parabola, and maybe at this point a line is tangent to it. Okay, and you can find what the, this is a derivative here, and you can do all sorts of fun calculus stuff later with tangents. But for now, we are just talking about a line that touches a circle at exactly one point. So that is the first definition on your notes there. Now, some properties of a tangent in a circle. So I've got on your notes, what do you think is special about a tangent line and the radius? So notice, as this thing is spinning around, this thing is a tangent line. It's always connected at that one point right there. And here's the radius. What sort of relationship does it look like exists between a radius and a tangent? And if you were to say, well, I believe that they meet at a 90-degree angle, that they are perpendicular, then you would be correct. So in your notes, it says the blank and the tangent line, we mean the radius and the tangent line, will always make a, you can say 90-degree angle, a right angle, whatever term you want to throw into that second blank on your notes. So let's look at an example here. DE and FE are tangent to circle G, and we identify the circle by its center. So this is circle G here, at points D and F. So D and F are what we call points of tangency. You might hear that referred to as. Okay, so DE is tangent to circle G at point D, and EF or FE is tangent to circle G at point F. If angle DEF is 56 degrees, what is angle DGF? So here is our question mark angle here. Now we just referred to a property that said a radius and a tangent are perpendicular. So if this is a radius, which it is, and this is a tangent, which it is, there's a 90-degree angle here. Likewise down here at angle GFE, this is a 90-degree angle. We really have a quadrilateral here. Specifically, this will be a special shape, which you could probably deduce what shape this probably is, a special quadrilateral, but we'll get to that point soon in the notes. Now, all quadrilaterals have 360 degrees, so subtract away our two 90s, subtract away our 56, and we are really subtracting away 236 degrees from 360, which leaves us with 124 degrees for our angle DGF. Now, how do you really know if a line is tangent or not? Well, let me show you something. So here right now, angle ABC, boom, 90 degrees. It is tangent. AB is tangent to BC. Now notice the lengths of our three pieces here, of our triangle, that if we connect our radius to our tangent and then connect, the end of our tangent back to our center, we make a nice triangle here. And if that's a 90-degree angle, this is a nice right triangle. And what type of relationship have we discussed about the side lengths of a right triangle? I believe we have talked about the Pythagorean theorem. So if I take my two legs and square them, so if I took 4 squared plus 6.93 squared, that is 64. And is that equal to my c squared, my hypotenuse squared? It is. Okay. Now watch what happens when I move point B to make this not a 90-degree angle. And if it's not a 90-degree angle, it's not going to be tangent to the circle. Watch what happens to the Pythagorean theorem once I slowly move this slightly. So notice, no longer a right triangle, which means the Pythagorean theorem no longer works. So if the Pythagorean theorem works, let's see if I can actually move this back to exactly 90, which I doubt I will, and I'm not really going to waste too much time here trying in my futile attempts to get exactly 90 again. But you can see that as this approaches 90 degrees, your a squared plus b squared value and your c squared value should be the same in the end. So jumping back to the notes here, if the Pythagorean theorem works, then the triangle is a right triangle. If the triangle is a right triangle, then we can say we've got a tangent line to our circle. Okay, so this is kind of like the transitive property, if you will. We're saying we'll call A the Pythagorean theorem, B a right triangle. Here we have B right triangle, C tangent. So A implies B, B implies C. So if the Pythagorean theorem works, we can say that we've got a tangent line. If the Pythagorean theorem does not work, we do not have a tangent line. So they work together in that way. So let's look at an example. So second example here. Is AB tangent to circle C, which we mean this circle, at point B? Is this the point of tangency? So we want to see, does the Pythagorean theorem work? Is there in fact truly, I'll put question mark here, a right angle? So we want to check. Well, let's call the 8 our A, let's call the 15 the B, and opposite our right angle, this must be our C side. Now this says this much is just 9, but I need to know, well, how much extra do I need to add on to this 9? Well, if you notice, this piece right here is really a radius of our circle. And over here we said this is a radius, which is 8. So this whole C piece is really 17, 9 plus the 8. So we need to check, is 8 squared plus 15 squared really equal to 17 squared? And if you recognize this is a Pythagorean triple, it does work out. But just to show you real quick that it really does work out, 64 and 225 indeed makes 289, which is equal to 17 squared, which is 289. So our conclusion is AB tangent to circle C at point B? And we would say yes. That is true because the Pythagorean theorem does work. And if the Pythagorean theorem works, we have a right triangle. If we have a right triangle, we do have a point of tangency at point B. Now, if two segments are tangent from the same point, so for example, if AC is tangent to this circle and CB is tangent to this circle, and they both come from the same point, point C, what do you think is true about these two segments, AC and BC? And you might think, I believe they might be congruent. I mean, just looking at these, it looks like it's pretty legitimate that that's the case here. Now let's discuss why that's true. Let's do a quick little proof here. Okay, what we want to do is we want to show that AC is really congruent to BC. All right, now things that we have to work with here. Let's draw in a couple radii from O to A and O to B. And we know that all radii in a circle are congruent, so we can put congruent markings on there. And since these are already tangents, we can go ahead and put right angles here and here. Okay, so far so good. An extra line that we will draw in will be from O to C. And the reason why we do that is because now we have two triangles here, two right triangles. And if we can show that these two triangles are congruent to each other, then that means everything else about those two triangles must also be congruent by CPCTC. Now this OC is really reflexive to itself. So if we look in both triangles, what shortcut do we have? We might go, oh, we get ASS. Oh, no. But this is the special ASS because the angles are 90. So these two triangles are congruent by HL. So AC must be congruent to BC by CPCTC. So we can conclude that two tangents from the same point outside of the circle are in fact congruent. Okay, and a fun way of knowing this piece of information here is I've had students in the past look at this sideways. Oh, if I can get sideways here. Come on, sideways. Whoa, 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 crazy. Okay, there we go. There we go. And they might look at this and go, hey, look, we can make a face. Hey, hey. And hey, you like going to parties, right? So we'll call this the party hat theorem. You guys remember going to parties when you were kids and you wear the stupid little like cone hats and then there's that elastic band that goes underneath your chin? Yeah, it's the same thing. Pretend this guy's a hat. This side of the hat is going to be congruent to that side of the hat. So we call this the party hat theorem. Party on, Wayne. Party on, Garth. Next up on our list, couple vocabulary terms which we may have used previously, but I definitely want to emphasize this time. The triangle is what we're going to call circumscribed about the circle. And what that means, circumscribed, means it's drawn outside so that every side is touching drawn outside so that every side is touching every side of the shape inside. So if the triangle is drawn around, if you will, the circle, it means that that each side of the triangle is touching the circle at exactly one point, aka each side of the triangle is tangent to the circle. Now, inscribed is the other way to talk about the circle with the triangle. The circle is really drawn inside the triangle, but it's not just drawn inside like, oh, look, hey, look, this circle's inscribed. It's drawn inside the triangle. It's got to be drawn in such a way so that every side of the shape that's outside of it is touching at least one point, or it's actually touching exactly one point, I should say. Okay, now I could, for example, inscribe a square inside, inscribe a square in a circle so that each corner is really touching the circle at exactly one point. Okay. So it doesn't have to touch each side. That would be kind of impossible for each side of the square to be touching the circle. That really wouldn't make too much sense there. But typically we're going to be talking about either quadrilaterals or maybe triangles inscribed in a circle, or we might be talking about a quadrilateral or a triangle drawn outside or circumscribed about a circle. All right, almost done here. We got two more examples. Number 3, AB, BC, CD, DE, EF, FA. So each one of these 6 little pieces of this big triangle are all tangent segments. The perimeter of triangle ACE all the way around is 60. BC is 10, check. EF is 8. What are the lengths of all the other segments? Now, one thing to notice here, if I kind of cover up part of a problem, if I covered up, let's say, these other 2 sides here, this kind of looks like my party hat theorem, right? I've got 2 tangents coming from the same point that go to the same circle. So these 2 pieces are congruent. So let's label that. Oh, no, wrong way. Nope, too much. There we go. So this piece is 10, and down here we have the party hat theorem. So if this side's 8, this side's 8. All right, now let's come over here. Well, crud, we don't know either one of these 2 sides. But what we do know about these 2 sides is they are the same. So let's call them x and x. Now the other piece of information we haven't used in this problem is that the perimeter is 60, which means the distance all the way around. So we have x and x makes 2x, 10 and 10 makes 20, and 8 and 8 makes 16, and we know all that needs to be 60. So let's see, that makes 36, so if I subtract 36 over, that gives me 24, and divide that by 2, so each one of these 2 pieces must be 12 and 12. And there now are all 6 segments of that triangle. And the last example, let R be the radius of a circle inscribed in a triangle whose sides have lengths 18, 80, and 82. Determine the value of R. And a hint I give is that the triangle is a special kind of triangle. Now, with sides of 18, 80, and 82, we could say, well, let's see, 18, 80, and 82. We could test out the Pythagorean theorem And see if this is equal, that means we're dealing with a right triangle. If it's greater than, if 18 squared plus 80 squared is greater than 82 squared, then we're dealing with an acute triangle. And if 18 squared plus 80 squared is less than 82 squared, then we are dealing with an obtuse triangle, which I believe we did this earlier in the year. Maybe, maybe not. I can't remember. So really, I just want to test this ultimately. Do I have a right triangle? So let's check that out. Well, 18 squared, that's 324, and 80 squared, that would be 6,400. So add those two things together, and I get 6724. So question mark, question mark. What is 82 squared? My calculator gives me 6724. So that means I am dealing with a right triangle. So let me draw a right triangle. Rather, let me design one. Let's make this bad boy right. Okay, so we have a right triangle. There's my right angle. And I have a circle that's inscribed in this thing, which means when I draw my circle, it's going to be a really crappy looking circle, but it's okay, that it's going to be tangent to each side of the circle here. Okay, so we'll call this whole thing, there's my 18. This has got to be my 80, so my hypotenuse over here is 82. And we have a radius of r. So this really isn't helping out much. So that's r. And maybe I draw it over here to that side. There's r. Maybe I draw it over here to that point of tangency. That's r. Now, do you see why I drew it to the points of tangency? Maybe, maybe not. This radius down here, when it touches this side 18, this is tangent, which means this is a right angle. And this radius over here, when it touches the side of 80, it's tangent, which means it's 90 degrees. So notice this kind of quadrilateral right here. All right. If I've got three 90-degree angles, how big does the fourth one have to be? It's got to be 90 degrees as well. It doesn't really look like it in this picture, but it must be. So I have a quadrilateral with four right angles. Okay, so that could be a rectangle or a square. Well, adjacent sides are congruent, which means the opposite sides are also the same values, that this is r and that's r. So this is really a square. Okay, where are we going to go with this, Mr. G? I'm so glad you asked. If this is r, what's the leftover piece of this? Well, it would be 18 minus whatever r is. Okay, now do we go up here and label this 80 minus r? Not quite. We're going to wrap around this whole thing till we get back to the r. So this little piece right here, well, how long is it? Oh, party hat theorem. This piece and this piece should be the same. So if that piece down there is 18 minus r, so is this piece. Which means how long is this leftover tangent piece here? Well, it would be 82, the whole thing, minus that little tangent piece down there. So I need to kind of distribute my minus sign. So I have 82 minus 18 plus r. 82 minus 18 makes 64 plus r. So this guy up here, from here all the way to there, that is 64 plus r. Party hat theorem kicks in again. It says this piece and this piece are the same. So if this is 64 plus r, so is that. Now what we want to do is we know this piece is r, but we can also talk about what this piece is when we have 80 minus whatever 64 plus r is. So again, distribute the minus sign. We got 80 minus 64 minus r. Well, 80 minus 64 is 16 minus r. So we're really saying that this piece down here, which we've already called r, can also be called 16 minus r, that these two things are equivalent to each other. Therefore, we may set them equal. So 16 minus r is really equal to r. Add the r over. We got 16 equals 2r. Divide by 2. The radius of this bad boy circle that's inscribed in that triangle is 8. Yeah, I'm sure I'm going to be answering some questions about this one tomorrow, next day in class. But If you need to rewatch that part, rewatch it. See if it makes any sense the second time you see it. That is all for the first video. I hope this didn't last too long. I hope you guys are still awake. And we'll try something special next video. Make it a little spicy. All right. Peace out.